Hey class, so this is for that AP practice problems pages 82 and 83 in our book. So I want to start us off here looking at our first problem. As I look at our first problem, it says up here that two of these choices can be correct. So I'm going to be looking for a position, and this position versus time graph, I want to see when these objects have the same average velocity during these time intervals, 0 to 2 seconds, 2 to 4, 4 to 6, 6 to 8. So if we recall, velocity is the slope of your position versus time. So I'm going to take this ruler, a straight edge, something so that way I can see for this. And we're going to have two of these answers. So I'm going to start off by looking between my 0 and 2 seconds. So if I go to my 0 seconds position, I want to get one end of my ruler here, and I want to get my other end of my ruler right here. So it looks like between 0 and 2 seconds, that's going to be an acceptable answer because it falls right on that average velocity line. Now I'm also going to check between 2 and 4. So if I go once again to 2, and then I want to take it to where the 4-second mark is, right about there. So now my ruler is getting a different slope than the average velocity. So it's not going to be letter B. And then I'm going to go between 4 and 6 seconds. So 4 right here, and then the 6 is right there. So it looks like now my ruler is going parallel almost with the average velocity. So I'm going to say letter A, 0 to 2 seconds, and 4 to 6 seconds for letter C is also having the same average velocity. And then I'm going to come back down here. I want to try between 6 and 8 seconds. So I'm going to go to 6, and then 8 is up here. So between 6 and 8, now I'm getting a much higher velocity here. So this is a much greater velocity than that average velocity. So we can see here that the answer would be A and C. So now as I continue, now I'm going to go on to question number 2. So as I look at question 2, we got 4 toy cars, and they start from rest at the same location. They all start from rest right here. And they're going to be moving in the positive x direction as shown in this image. So in each case, the time intervals recorded are between these positions are the same. So there's going to be a car here, and then like a second later here, another second later, another second later, another second later. For the same thing for B, 1 second later, 1 second later. So they're having the same time intervals, it's just now they're at different positions. So we're asked for which car is the value of this acceleration certainly not constant. So we want to find the one that does not have a constant acceleration. So in thinking about this, I was trying to think, well, how can I show this? So what I started to do is I started to, create some data tables. So for car C, I did C first. I don't know why. I started at C. And at time equal to 0, there's at position 0. Time equal to 1 is at 1.5. Time equal to 2 is at 6. So I went 1.5. There's 6. And then I did the same thing for D, 0, 0. And then at time equal to 1, I would say it's 2 out. And then at time equal to 2, it's 1, 2, 3, 4, 5, 6, 7, 8. And that's 8 out. And so that's how I got to that for D. And I did the same thing for A, where I have the time and the position. Same thing for B, time and position. So with that, then I was like, well, I can graph these, I can do it by hand, but this is where I really like using Google Sheets. So I use Google Sheets because I really wanted to use what I have. So I know if I have this as a graph, I want to get that t squared. I want to linearize my graph. So I took this and I just wrote in an equation where I wrote in equals t squared, and then I get my t squared over here. So then I'm seeing that I get these values of position versus time, and then I plotted a graph. And so I have my trend line here giving me an r squared value of 1 for graph C, and a r squared value of 1 for my car D. And I continue down. My r squared for B was not exactly 1, but 0.998 is pretty close. But I'm going to come back to this, and maybe this will help us when I come back to that t squared graph for B. And then I get down to A, and A also has an r squared of 1. So what I'm going to do is I'm going to write in an equation here where I'm going to go equals to position divided by time. And if I do that, and then I drag this down, I see I have a change in my position with respect to time squared is different for each interval of time here for graph B. So that's why I even highlighted this, because I wanted to make sure I got this right. And I'm going to try it for graph A. Maybe it's different for A. I'm going to take my position, divide it by time. And I get a 0.5 for A. And if I go down, my change in position over my change in time squared, I'm choosing time squared because we're dealing with accelerated motion. They're all at 0.5, so it's definitely not A. I'm going to come up to my car D. Well, it's going to take my position, divided by time squared. I get a 2, and same value for both. And then I'm going to do the same thing for car C, equal to position divided by time squared. And I get a value of 1.5. So that means, really, all these graphs, except for B, have a constant change in position with respect to time squared, except for B. And so that's where B does not have a constant acceleration. So I used my graphing abilities, my graphing knowledge here, and my linearization of time squared to answer this question. So for this one, you had to use that squared dependence. So that's going to bring us up here now to question number 3. So for question number 3 now, we're getting asked, suppose we have a projectile on a different planet. So we're going to get something on a different planet, and we're going to shoot it up. And so that's what we see here. It gets shot up, and then it comes back down. And it takes 3 seconds to go up. To come back down takes 3 seconds. But at its highest point, we see that it gets up to 18 meters at its most highest point. And what we're trying to use is we're going to try to use its vertical position with respect to time to find the magnitude of that acceleration due to gravity. That's what we've got to try to find here for this number 3. So the equation I'm going to use for this is going to be that change in y going to equal to that 1/2 at squared plus v naught in the y times t. I could write out the plus y sub 0, but I'm talking about a change in y, so I'm not going to include this. And it didn't tell us anything about the initial velocity. It didn't say anything about that at all, but I do know that at the absolute highest that this projectile went, it has a 0 velocity. So what I'm going to do is I'm going to say, well, if my initial velocity is 0 meters per second, then I can drop this whole term. So that's going to leave me just with this change in y going to equal to this 1/2 at squared. So in other words, if I come back to my graph, if I drop it from this highest point all the way down to the ground, it's going to go from 18 meters back down to 0. So now I also know my change in y is going to be 18 meters. So I know it's going to fall 18 meters. And how long is it going to take? Well, if it took 3 seconds to go up and down, that means it took 1.5 seconds to just go down. So I know now my time is 1.5 seconds. So I know my change in y, I know my time, I can get my acceleration. So I just do some algebra. My a is going to equal to 2 times the change in y divided by t squared, where 2 times 18 meters divided by 1.5 seconds quantity squared. What we get is this, I think, is 16 meters per second squared. Let's see if that's an answer. Hot dog, look at that. Question number 3 is letter D. So now we're getting number 3 to be letter D. Now, once again, just to recap, when it's at its highest point, it has a 0 velocity. So you already know its initial velocity then. That's what's really cool, because you know its initial velocity at its highest point. It's 0. and then it's fallen down. And you know how high up it went, so you know how far down it's going to go. And if you know how long it took to go the whole time, that means you know how long it took to fall, because it's going to be half the time up and half the time down. So now let's move on to question number 4. So number 4, this is using this graph v squared and position. Once again, now we're trying to find some acceleration. So we're trying to use this to find some acceleration here. That's what we want to find here in number 4. So if I see this v squared, I mean, I can try to square some of my stuff to get it, but we also know an equation from our equation sheet that this v squared is going to equal to v naught squared plus 2a x minus x naught. So if I look at that, now I kind of have an idea, because at time equal to 0, I know my initial velocity is squared. So when time is 0 seconds, that's when I can find my v naught. And time, or this position 0. So my v naught now, my initial velocity is going to be 50 meters per second, or meters squared per second squared. Now this isn't necessarily time equal to 0, but we're saying over this change in position. So I can assume that's time equal to 0, but we're not given time. We don't need time. So I'm even going to get rid of that, just so we're not confused anymore. But just based on the graph, the initial velocity here is that 50 meters squared per second squared, because that's what velocity squared is. I'm going to fix the book. Meters squared per second squared. So now that I know that, I can also look here on my graph. Well, my position, x, if I go 4 minus my initial position, 0, so my delta x is going to be 4 minus 0, all in terms of meters, so that's going to be 4 meters. And if I know that, then I know my initial velocity, I know my change in position. I'm trying to find this acceleration, so maybe now I can find this v squared, where this v squared at the end of my change in position is at this 10. So my v final squared is this 10 meters squared per second squared. So now I just got to get another little bit of algebra, because, or sometimes algebra isn't always good. I know sometimes you just want to plug in the numbers, so let's do that. So I know this final, that's this one right here, I know I get 10. 10 is going to equal to what is initially 50 plus something, plus 2 times the acceleration, this is what we were trying to find, times 4. So if I told you 10 equals to 50 plus something, that's something you already know has to be a negative. This already we know has to be a negative, because 50 plus something equal to 10, well, we know that has to be negative. So I'm going to subtract this 50 on the other side. So I get a negative 40 is going to equal to this 2a times 4. Well, 2 times 4 is 8. So 8a is equal to this negative 40. Well, now I'm going to divide by 8 on both sides. So I get a negative 5 is equal to my a. And then my units are meters per second squared. So let's check to see. Look at that. Number 4, a. And that's kind of good. I'm glad I got the negative, because I see this even has a negative slope on it. So with that negative slope, it tells me I should have something with a negative acceleration here. Good. So now let's move on to number 5. So as I move on to number 5, this is going to be in reference to this graph. So we're going to reference this graph for 5 and 6. So in number 5, it's saying, at which of the following times does an object have the greatest displacement from the start? So what we're being asked to really think about as we're working through this number 5 and 6 is, while we know for a velocity versus time graph, the area I think that's pretty close to like what they drew. Yeah, not bad. The area underneath it is going to give us that displacement. So the area up here, this is going to be a positive displacement. So this is going to be all a positive displacement. This is the only time when it's going backwards. So that's going to be the negative displacement down there. And then we're going to get more positive up here. So as I look at this graph, like there's very little going backwards. Very little going backwards. A lot going forwards, and then you eventually come to a stop and go backwards just a little bit, and then you go forwards for like a good amount. Like you go pretty fast going forwards. So the greatest displacement is going to be where we have the greatest total area. So if I look between 0 or going to 1 second, I only have this part shaded, and there's all this right here. So going out to 2 seconds, I got all this shaded up. If I go out to 3 seconds, now I'm going to have some of it going backwards. So now we're moving backwards a little bit. That's not the greatest displacement. But if I go out all the way out to 4, yeah, I did go backwards a little bit, but going out to number 4 seconds, we went farther, faster, farther forwards than even this little part going backwards. So the area underneath this is much bigger than the area underneath that 3 second. So yes, that is going backwards a little bit, but this above 0 line is really big. So that's why number 5 is going to be that letter D. And then we're looking for the time interval in which the object has the greatest acceleration for number 6. Well, once again, we're going to look at a slope. So here I just take my straight edge and I want to go between 0 and 1 second. 0 and 1 second, I have a really steep slope. That is my acceleration there between 0 and 1 seconds. Now if I go between 1 and 2, now I'm going to have like a slope, but it's slightly negative. So that's not really going to be that good. If I go between 2 and 3, and to 2 and 3, now it's still just slightly negative. And then from 3 to 4, it's there, but not as dramatic as it was for 0 to 1. So like this is going positive, it is going up, but it's not as dramatic as it was between 0 and 1. So I'm going to say between 0 and 1 seconds, that's when we had that greatest acceleration. Now this is going to lead us to this FRQ. As I get to this FRQ, now we got a student driving in the road. Oh, that scares me. And as they're driving in the road, they see a red light. And so they're driving here with an initial velocity. And once I start seeing something, I like to write out what it is that I have. So I like to write out that I have an initial velocity. And I like to just kind of like give myself a positive. They didn't tell me I'm going backwards or forwards or anything, but I like to be positive about myself. And I see the red light, and I'm going to apply my brakes. So I already know I'm going to apply my brakes. So my acceleration is going to be negative because, well, I'm not going to speed up. Now, it'd be like me saying, all right, I know I want to beat that red light, and I could hit the gas and get through it, but no, you hit the brakes. So that's why you're slowing down. So your velocity should go down to 0. So that's what it even says here. So the student decreases their speed at a steady rate. So that means a constant acceleration, a constant negative acceleration. And my final velocity, what I end at, is going to be 0 meters per second. So my final velocity is going to be 0 meters per second. And it took me a total distance, d. So my displacement is going to be this d. That's the total distance that it took. So now it's saying, well, let time equal to be 0 when that's the time when you first apply the brakes. And what we're going to try to do now is apply our graphical knowledge to this. So I'm not so bold to make my graphs in pen, so I'm going to make it in pencil. And so what we're going to try to do is sketch our displacement versus time graph, a velocity versus time, and an acceleration versus time. So you could start anywhere you want to start. I know, like, sometimes looking at all this, you're like, I have no idea where to start. And I know sometimes that's how it is. But I'm going to start here from velocity because I think this is going to be the easiest place for me. I know I have a positive initial velocity, so I have a positive initial velocity. And then I know after some time, I come to a stop and I have a zero velocity. So after some time, I have a zero velocity. And that means, where's my straight edge? That means now my graph has that negative slope, which matches up to what we were seeing here. I know I should have this negative acceleration. I see this negative slope matching up to what I thought with that negative acceleration. So I have a constant negative slope. So I have now my constant negative acceleration. Okay, good. So I can then, now I have my acceleration, I have my velocity. I can get it over here to my position versus time. Well, I know I'm going fast in the beginning. So in the beginning, I'm going fast. So I have a big change in my position. Then at the end, I stopped. And then we could even say I'm sitting at that red light. So we could even say we're just sitting there. So I'm even putting that on 0. Because you don't just stop at the red light and then you disappear. No, you sit at that red light. All right? So then after some time, I'm going to be at the red light. If this is where the red light is, then I'm going to be here. I'm going to stay here. I'm going to be there for a good minute. And I stay there, and I'm not going anywhere. That's a long red light. So if I'm starting fast to a stop, I'm going to get this curve here because of that parabolic motion that we're talking about. So now I have my position versus time, velocity versus time, and acceleration versus time graphs. Now this is going to bring us over here to letter B. It says the total braking time is 4 seconds. So once again, I like to write stuff out. So now if that's for letter A and for letter B, the time to brake is going to be 4 seconds. Does the car travel a greater distance in the first 2 seconds or in the last 2 seconds? And in this, we want to try to explain your reasoning in a clear, coherent paragraph length response. So in other words, we got to try to explain why we think what we think. So it says that we can refer to graphs, equations, or motion maps. Well, we just drew some graphs. So I'm going to come to here and I'm going to make some graphs. If I say that this right here is the 4-second mark, if I say this right here is the 4-second mark, and halfway 2 seconds, halfway 2 seconds, what we're trying to see is where, did we go farther distance in the first 2 seconds between 0 and 2 seconds, or did we go greater distance between the 2 and 4? So between 2 and 4, or the 0 and 2, 0, 2. So just based on our graphs, if I was to bring this up to here and bring it over to here, this is the distance here in the first 2 seconds, between 1 and 2. This part is that change in the distance between 2 and 4. Like, it's not even close. These first two right here, that's not even close. This is way bigger than this second one over here. Now, you can use that. You can say, well, based on my graph, I can say that. But also, sometimes, if you're going to use your graphs, use more than just one. Well, we know the area underneath this velocity versus time is that displacement. So if I have the area in the red and the area in the green, just visually, you can tell which area is bigger. Just visually, you can tell which area is bigger. So can drag this over here, I know that this is my velocity at the 2-second mark. So I could even call it v sub 2. I know my velocity at the v sub 2 is less than my initial velocity. And I could argue the area here that, well, this area is larger than this area, because this is just a triangle, 1/2 of that v2 times 2 seconds. That's not even going to equal to v2 times 2 seconds, because now this right here is a square, where if we were to call that, the area of that triangle of the red is that area right there, because that's v2, the height of v2, and 2 seconds. So this is at least, the green area is at least double the displacement than the last 2 seconds, at least. Now, we're not even taking into account this part up here. So just using my graphs, I can talk about the area underneath the velocity versus time graphs, or I could even talk about how my displacement versus time has a much greater change in the first 2 seconds than in the final 2 seconds. So I'm hoping this here really helped us with this AP practice problems. If you have more questions, don't hesitate to ask. Thank you very much, class.